In this video, we are going to finish the topics of the first part of the video series for chapter 6. Now we are going to talk about the different types of illustrations that can be utilized for monosaccharides. The first one is an image that you guys observed before in the previous examples that we did for the classification of monosaccharides when it comes to number of carbons and carbonyl functionalities or functional groups. This type of representation, which is very common, is known as a Fischer projection. A Fischer projection was devised by Emil Fischer in 1891, and it is a two-dimensional representation of a three-dimensional organic molecule. Because remember that monosaccharides, carbohydrates, there are biomolecules that, because they contain carbon, they are known as organic molecules. Fischer projections were originally proposed for the depiction of carbohydrates and used by chemists, specifically organic chemistry or organic chemists, and in biochemistry. So overall, understand that when it comes to these illustrations, when we look at the molecules, the carbon atoms that are at the intercepts of the horizontal line versus the vertical line that we have in the molecule represent carbon atoms. So if we are given a Fischer projection, remember that these illustrations have carbon atoms at each of the intercepts. And you can number the carbon atoms after you have placed them at the intercepts. This, in a way, is a mix of having a condensed structure combined with a skeletal structure. Let's now proceed to talk about the most common monosaccharides that exist in the world around us, starting with glucose. Glucose, we can observe that this is its structure. It is found in fruits, in corn syrup, and it's even found in honey. We learned previously how to classify monosaccharides in terms of their carbonyl functionality and their number of carbons. So when we look at the structure of glucose, we can observe that there is an aldehyde, and there are 6 carbon atoms, 1, 2, 3, 4, 5, 6. So that's why glucose is known as an aldohexose. Its chemical formula, since it has 6 carbon atoms, that means that N equals 6 for the general chemical formula, CnH2O(N), means that glucose has the chemical formula C6H12O6. Glucose is also known as dextrose. And whenever sugar has been or needs to be detected in our blood, sugar, specifically glucose, is the sugar that is being detected. Glucose is very important because if we look overall at larger carbohydrate molecules, including disaccharides or polysaccharides, is going to be the building blocks for these molecules. So we can see that glucose is present in the disaccharides sucrose, lactose, and maltose, and it is even present in polysaccharides, including starch, cellulose, and glycogen. Next, let's talk about galactose. Galactose is also an aldohexose. Remember, aldo because there is an aldehyde in this structure. Hexose because there's 1, 2, 3, 4, 5, 6 carbon atoms in the molecule. That means that the general chemical formula for galactose is also C6H12O6. Galactose, out of these monosaccharides, is the only one that is not found free in nature. So you don't see galactose as a unit by itself. It exists in nature because it can be obtained from a disaccharide. And as a reminder, a disaccharide is going to be a carbohydrate with 2 units of monosaccharides. Specifically, lactose is the disaccharide where galactose can be obtained from. Now, when we compare the structure of galactose and of glucose, it is important to note that the difference is structurally for these molecules are actually at carbon number 4. So we can see that in glucose, the OH group is pointing towards the right. And in galactose, the OH group is pointing towards the left. Because of this difference of where the OH is pointing, because all the other atoms are actually pointing in the same direction, except for the OH group on carbon 4, these 2 molecules are going to be different from each other just simply by the fact of this position of the OH. And you can see that it is a brand new monosaccharide, that the simplest difference of having an OH pointing in a different direction, it actually gives you a different monosaccharide. When it comes to determining, okay, so what does this mean in terms of things being isomers? For sugars, it's specifically known that if you have sugars that, or monosaccharides, I should say, that are different from only one position, okay, in their structure, where the OH is pointing differently, those are known as epimers. So what this means is that glucose and galactose are epimers, meaning that it is a specific class of isomers that are present in the structures of monosaccharides. Lastly, we have fructose. Fructose can actually be obtained from sucrose. Different from glucose and galactose, fructose is actually a ketose sugar. So it's a ketohexose. Similarly to them, it has 6 carbons. So that means that its general chemical formula is going to be C6H12O6, but different from them, we see that there is a ketone motif. So we have a carbon chain, we have a carbonyl, we have another carbon chain. So that's why fructose is a ketose sugar. When we compare fructose and many other monosaccharides, including glucose and galactose, fructose is actually sweeter than all the other monosaccharides in existence. As you can see, it's even sweeter than sucrose, which in everyday life, sucrose is actually what we use as table sugar. One more thing that has to do with isomers and monosaccharides. If we think about stereochemistry, thinking about the presence of chiral centers in these structures, it is important to note that there is chirality present in monosaccharides. That means that if there are chiral centers and we have monosaccharides that are mirror images of each other, we can have enantiomers of the different monosaccharides. How do we know? And how do we have a designation for monosaccharides that are enantiomers of each other? Well, we have a specific symbolism for those. When it comes to monosaccharides, the way that we designate the pairs of enantiomers is given by the letters D and L. The designation D and L are actually assigned by looking at the position of the OH group that is on the chiral carbon that is the farthest away from the carbonyl group in a monosaccharide. If your OH is pointing to the left, then the L designation is going to be given. If the OH is pointing to the right, then that means that the designation of that monosaccharide is going to be the letter D. Many years ago, I actually received this image from one of my friends from graduate school, which is just showing the illustration of this dichotomy between D and L. And we can see here that we have Samuel L. Jackson and Samuel D. Jackson, just basically utilizing an image in which one is looking towards the left and one that is looking towards the right as a reminder of what is L configuration versus D configuration. But if we go back to the molecular model or the structure that we have above the image, we can observe that when we look at these two enantiomers of the monosaccharide erythrose, if we look at how did we get that L designation for erythrose versus D designation for erythrose, we need to investigate what or where is the chiral carbon that is the farthest away from the carbonyl. First, let me illustrate by looking at L erythrose, the chirality that exists in the molecule. So first, I'm going to place the carbon atoms. There's a carbon atom right here. There's a carbon atom right here. Both of these atoms are going to be chiral. If we observed around the molecule, the carbon in the aldehyde is not chiral because it only has 1, 2, 3 groups. Because remember that the chain, so overall this area counts as a group overall. And any carbon that is chiral, it needs 4 different groups. So when we look at the first carbon that I wrote, let me number them because that will, I think, ease the conversation of the carbons that I'm looking at. So I already determined that carbon number 1 is not chiral, and I'm going to number this as carbon 2, this as carbon 3. So carbon 2, it is chiral. I'm going to use my highlighter tool to illustrate the groups that are there. So this will be group number 1. This is group number 2. This is group number 3. Lastly, this whole thing is group number 4. That's why carbon 2 is chiral. So I can put an asterisk next to it to determine that it is a chiral center. Next, I'm going to erase this work to illustrate why is it that carbon 3 is also chiral. Carbon 3 is chiral because when we look at the groups that is around it, it has this whole carbon chain is attached to hydrogen, is attached to OH, and is attached to this group. That's why carbon 3 is chiral. Erythrose is actually a tetrose. Let me label the 4th carbon atom that is here. Now, carbon number 4 is not chiral because it is attached to 2 hydrogens. And from our previous discussions, if a carbon atom has 2 groups that are the same, then it cannot be chiral. So in this molecule, carbon number 2 and carbon number 3 are your chiral centers. That's why I put asterisk next to them. In L-erythrose, we can see that the OH is pointing towards the left. Since it's pointing towards the left, that's why it is an L isomer. Let's look at the structure of D-erythrose. Similarly, it has 1, 2, 3, 4 carbon atoms. Determine how many chiral centers are in D erythros. Just like we observed in L erythros, the chiral centers are carbon 2 and carbon 3. But because carbon 3 is the farthest away from the carbonyl, which is on carbon 1, then that's the ones that determines the L or D designation. And in this case, since OH is pointing towards the right, then that's why this is D erythros. If we go back into the monosaccharides, glucose, galactose, and fructose. I want you to take a moment and determine the D or L designation for these molecules. Additionally, let's determine how many chiral centers are on each of these monosaccharides.